So now we have everything in place to define sparse squared quadrature rules. And remember, now we have to put together the ingredients. So using the notation developed so far, the tensorized quadrature rule can be written as this. So I have the d-dimensional rule. So we write it like this: QL1 direct product G, and then I can write it down like this. So max K less than or equal to L, and then I write it in terms of the deltas, KD1 of G. So where this K is a multi-index, in n to the power D is a multi-index with max K is actually the maximum of I running from 1 to D of the Ki. And why? Well, the tensorized rule consists of all telescoping sums in all dimensions. So missing a bracket here. So I write the one-dimensional rule as a telescoping sum, each of them, and then I multiply all of these terms together and put them into one sum, and then I get all combinations of all the different quadrature rules. So this is why I can write it like this. So the tensorized rule consists of telescoping sums sums in all dimensions. All right. Well, and this resembles max degree already. And now I can write something down, which is now supposed to be the sparse grid quadrature formula. And I just do something with the multi-index. On the other hand, the sparse grid quadrature formula level L in RD is given by so QLD G, and the only difference is that here I put the absolute value of the multi-index K. It's supposed to be less than or equal to L plus D minus 1, and I'm going to explain this in a second. So delta K1, 1 cross delta KD, 1 applied to G, and the absolute value of the multi-index is the sum of all absolute values of the entries. So the one norm instead of the infinity norm. And again, so that's the only difference. So the sets in which the index is run, or the multi-index is run, are this one for I of L for the sparse case, so K and N to the D, sum I from 1 to D, Ki less than or equal to L plus D minus 1. That's the sparse case. And I of L is K and N to the D, such that the maximum of Ki is less than or equal to L. and I from 1 to d. And that's the tensorized case. And why do I have this weird thing here? Well, actually, it needs to scale with dimension d. And if the level L is equal to 1, then 1 for every index is allowed. Yeah. So if all the indexes are 1, I want this to be level 1. And so that explains the -1. Otherwise, it needs to grow with L, and it needs to grow with D. So we see this in another example. If we look at D equals 2 and L equals 4, and I'm going to start writing this example here. D equals 2, L equals 4. Well, let's put this on the next slide. So I want to draw some pictures. So example D equals 2, excuse me, and level equals 4. And let's draw some pictures. So here are the sets of the multi-index for the sparse case and for the tensorized case, K2. So 4, 3, 2, 1, 1, 2, 3, 4. This is 1 and 1 here. 3, 4, 1, 2, 3, 4, 1, 1 here. So where does the tensorized run? It's very simple. All of these multi-indexes are allowed, so the maximum is 4. Yeah, so that's just what it means. And in the sparse case, yeah, so this is tensorized, and this is sparse. So in the sparse case, I'm running the sum up to L plus D minus 1. So L is 4 and D is 2. So 6 minus 1 is 5. So here in 1, it goes up to 4 because then the sum is 5. If this is 2, then it goes up to 3 because then the sum is 5. If it's 3, then it goes up to 2 because the sum is 5. And if it's 4, it goes up to here if the sum is 5. Yeah, so this is where the multi-indexes run in the sparse case. And now this, I'm not going to prove to you that sparse grids actually integrate polynomials of a certain total degree exactly, but you can kind of see it that the count is right from this picture here. If you now imagine all of the polynomials that you can form. So here I have x to the 0, x to the 1, x to the 2, x to the 3. Same here, y to the 0, y to the 1, y to the 2, y to the 3. Same here, x to the 2, x0, x1, x2, x to the 3, y to the 0, y to the 1, y to the 2, and y to the 3. So what do we get in terms of polynomials here? So the leading order ones is here x cubed. This is x squared y. This one here is xy squared. And this is y cubed. So you see the polynomials of up to total degree 3 on this diagonal. And down here you see the ones with lower degrees, total degree. And the max degree ones have a bunch of them in addition. So it's x cubed, y cubed, and this is x cubed, y squared, which the max degree polynomials of order 3 have in addition. So you see that these schemes here very much mirror the structure of the sets of total and max degree polynomials. Well, so let me make a note and then let's look at another example. So the nodal set of a sparse quadrature rule is given by this. Well, we translate the sum into a union. So it's the union L plus D minus 1 theta K1 1 cross theta KD 1. And well, let's draw the sparse grids. So how do they look like? And we take the sparse trapezoidal rule in 2D again, because there we can draw something. So the nodes of the nested 1D trapezoidal rule are these. So just in our notation, theta 1 1, that consists of 0 and 1. Theta 2 1 is 0, 1/2 and 1. Theta 3 1, 0, 1/4, 1/2, 3/4, and 1. Okay, and well, if we keep in our notation, so we take the same thing as before, L equals 4 in dimension, dimension D equals 2, then the nodes are, well, theta 4, so that's L in 2 dimensions. So that is theta 1 1 cross theta 1 1 union theta 2 1 theta 1 1 union theta 1 excuse me 1 1 cross theta 2 1. Yeah, so here both of them add up to 2. Here they add up to 3 in the indexes. Now we can add up to 4. Theta 2 1 cross theta 2 1 union theta 3 1 cross theta 1 1 union theta 1 1 cross theta 3 1. And then we have the sum equal to 5. So union with theta 1 1 cross theta 4 1 theta 2 1 cross theta 3 1 theta 3 1 cross theta 2 1, and finally theta 4 1 cross theta 1 1. Yeah, so what this says again, it's now a long formula. So how do I get the sparse grids? So I get it by this union, right? And first of all, I have level 1 in x dimension, level 1 in the y direction, level 2 in x, level 1 in y, level 1 in x, level 2 in y, and so on and so on and so on at all of these points. So let me draw them for you in a couple of pictures. Or maybe just, let's say, one picture which I fill by the points. So here's the x direction, here's the y direction, here's 1, and here's 1. So let's draw this as the square that it is. So if I now have level L equals 1 in both directions, then we have these points here, these 2 points here, and this point in addition. And what do we get in addition is if L is equal to 2? Well, I have those points, but I have now level 2 at the x direction, cross level 1 in the y direction. That adds up to 3. And now I get all pairs of points. These are all of these 6 points here. And then I get the same with a different color with those points here times, so level 1 on the x-axis times level 2 on the y-axis, so those points. And if I now take all pairs, I get this one in addition. So that's also L equals 2. Yeah, so it's in contrast to the tensorized grid, this point in the middle is missing in this. And then let's try the next one. L equals 3. So I get 3, 1. So on the x-axis, I get those points now. And on the y-axis, I get the level 1. So taking all pairs, I get those points. Now I can do, this was 3, 1. Now I can do 1, 3, so which is this point here, and now I get these points here. And now in addition, I'm gaining this point here and this point here. The other ones are just kept. So that's the other one. So that's let's maybe add this to the points. So that's 1 cross 2. That was 2 cross 1. That one was 3 cross 1. This one 1 cross 3. And then we have another one, and I'm slowly running out of colors. That's the 2 cross 2. So that would be this one here, and this one here, and also those points here. So here I'm getting some points in addition. So it looks like this. Yeah, so this would be the L equals 3 sparse grid, and now I can go one level higher, level 4, and I'm only going to spend one color on it because I'm out of colors here almost. Well, I'm pretty much out of colors. So let's try it nonetheless. Light blue, L equals 4. I get a refinement here. Let's try this. So it's level 4 in the x direction and level 1 in the y direction. So I only get the points on this axis and this axis because I'm taking those points here. Then I have the same thing here. So points in between. So that's 1 times 4. And then we get 3 times 2. So which points are those on the x-axis? This one, this one, this one, this one, and this one. And 2 is this one here. So I get, in addition, this point here and this point here. I also get this in the opposite direction. And this is my sparse grid of level 4. And you can kind of see where this is going. And I would recommend you do this construction by yourself. Maybe until 5, maybe you make it until 6. And These sparse grids also have another name in the literature. They are sometimes called hyperbolic cross, because in these grids you see crosses forming. Yeah, so I have certain points I don't have, and most of the time there is crosses forming. In the next level there would be crosses forming here, each of these corners, and then crosses, finer crosses and finer crosses and finer crosses, because we leave out some points in the middle. So this is how sparse grids can be constructed and how they look like.